that we can go. So this is an honor for me, because this is the first section of the joint seminar of OCIE and MPP seminar. So in fact, it's the first section of the MPP seminar, strictly speaking. And it is, the idea is to seminar is to join research and teaching. So the student of MPP are required to be part of the seminar, but the seminar is intended to be a research seminar. Sometimes there will be section for the philosophy seminar, sometimes there will be section from the quantum and the seminar, and sometimes will be section with mathematics seminar. For example, the next session will be by President Daniele Struppa, and will be a session of mathematics, even if we made it to count on the OCIE seminar in any case. Okay, so today is a section about something that is in the middle between mathematics, philosophy, and history of mathematics. There is not a lot of physics today, I'm afraid, but and the work is based on a joint work with Gil Férez, Jose is there, and Drew, that he should be there, but he's always distracted in the last time. Drew, I think that because of his dean offices, there are a lot of things to do. So, okay. And there is also Alberto Naibo, Jean-Michel Salanskis, that in this moment are in Paris and they are sleeping, so they cannot be part of today. So before beginning the part more on research, I want to tell something to the MPP student. The idea of the seminar is a triple one. The first one is to give an example of a scholarship, the example of scholarship presentation, scholarship talk, example that you should follow in your future life as scholars. I don't know whether I am a good example of scholarship presentation, but I do my best. In any case, other colleague after me would be certainly better example than me. But in any case, insofar as in my life, I gave a lot of presentation in scholarship event. I suppose that my way of giving a presentation is perhaps not the best way, but one of the ways that is admitted in the community. So try to take the good that there is and eliminate the bad that there is. One thing of the bad is certainly my English, but let's say I cannot do better. But I hope at least on the content, we can, you can take a good example. I try to make something that is not very technical philosophically speaking, not very technical mathematically speaking, but still something that could be of interest because of a lot of implication of both mathematical and historical, and also philosophical, perhaps a little bit less. The second purpose of the seminar for MPP students is to make you meet with scholars. So in this case, this purpose is null, because in any case you meet with me, but we will have other cases in which we will people, external people, and so you meet this scholar will be very important for you. And the third purpose is to make you take part of contemporary discussion in philosophy, mathematics, and physics, because it's not only a question of giving an example, it's also a question of make what is our job, that is scholars, and so to discuss current open questions in the different disciplines. So this is an open question, but this, by the way, this is an open question for how much? 2,500 years. And so we pretend, Jose drew the sleeping Parisian to solve a problem that is open for 2,400 years. Of course, this is not a very important philosophical problem, because otherwise we will claim for medal field. This is a small problem, but still is a small problem open from 2,500 years. And so we are very proud to give a solution. And now I know that this audience by email, there is what I consider to be the most important expert in the domain in the world, that is Victor Pampuchan. So if Victor said that is good, I'm completely sure that is good. If Victor said that is wrong, so perhaps he certainly, no. Drew said it is not wrong. So I wait from Victor, would say, but I totally trust the opinion of Victor Pampuchan that is, I think, on this matter is the best that can be in the world. Okay, so let's begin. The problem concerns postulate 4. Postulate 4 of Euclid elements says that all rectangles are equal. Okay, to be more precise, this is what the postulates say, and you find it. All right angles are equal to one another, but in fact, what we have to understand in modern terms is all right angles are congruent. Congruent, equal is as you cannot translate in another way than equal in English, but we have to understand as congruent in modern terms. So a question of congruence. And this postulate that tell us it is quite strange from the very beginning, and this strange character has been noticed from very all the time. Here I begin by Proclus, but I could have begun before Proclus, and Proclus himself mentioned Geminus, that is before him. Why? But for two reasons. The first reason is the postulate has a different logical structure than any other of the four postulates, the other four postulates. The other four postulates can be understood as constructive rule. This is clear for the first three postulates. From 2 points, you can construct a segment. From one segment to prolong the segment. This is a little bit complicated, but okay, in the first glance, we do not enter the details. It's a construction. You have a segment, you can have a straight line, more or less. Then the third postulate says that you have 2 points, you can have the circle with one of the points as the center and the other point of the circumference. So in fact, you have the radius and you can have the circle and the center. And postulate 5 is a little bit more complex to understood as a constructive rules, but there is a way to do it. It tells that if you have 2 segments, is if the sum of these 2 angles is related to right angle, then you can suppose that you can construct an intersection point. The postulate will say that there is an intersection point, that the 2 lines intersect. If you want to understand it constructively, you say that you can admit that the construction of intersection point. So the 3 one has clearly constructive rules. The 5th one is more ambiguous, but there is a way to understand it as a constructive rule. The 4th postulate, absolutely not, because the 1st postulate say all rectangles are equal. And this is a theorem. It's a theorem. It is the form of a theorem. It's not the form of a constructive rule. The form is the form of a theorem. And so this is the first strange thing. Before going to the second strange thing, for people that is not expert on the matter, I should say that a right angle for Euclid is not an angle of 90 degrees. Because if an angle was an angle of 90 degrees, the postulate would be trivial, of course, because a right angle is 90 degrees. So it would say that any angle of 90 degrees is equal to any angle of 90 degrees, and this would be tautological. What is important to understand is the definition of right angle for Euclid is that the angle is right when it is equal to its complementary angle, supplementary angle. Okay? So in this case, in this case, the angle is not right because this is not equal to that. In this case, it's equal because this is equal to that. But of course, you can say that the right is equal to that. But so if you have another one, the only thing that you can say is this is equal to this one. But you say nothing about the relation between this and this. You have no construction that allows you to compare this and this. So the postulates say that whenever you construct 2 complementary angles that are equal, so the 4 angles will be equal between them. So this is what the postulates say. And this clearly has the form of a theorem, not of a constructive norm. So this is the first thing that make the thing strange. And this is what Proclus said. This is the Greek citation by Proclus. One thing for the student here, normally when you write a paper, you should make much more precise references. In a talk, normally the references are very succinct because to question the editor, the translators would be long, but you should be able to give, if someone asks you where you take the text for, you should to say, this is page 188, line 15 of the critical edition of Proclus with my English translation. This is the Greek text and my English translation. And what Proclus says that if we grant that this postulate is so evident that it does not need of a proof, then according to Gimenius, is not a postulate but an axiom, since it assigns by itself an attribute to right angle rather than postulating that something is simply considered to the thought. That is a very ancient way to tell what I said before. It is the form of a theorem and not of a constructive rules. And so first point, but there is also a second point, because the second point that has been noticed in different occasions is the postulate is provable. The postulate is provable, and many different ways to prove the postulate can be suggested. And the difference, so to say that we can prove the postulate within a Euclid setting is not new. What is new that is pretended our proof is the only one that has been proposed in the 2,500 years that is perfectly correct without this setting, in the sense that the proof that has been usually presented have some reason for being contested. So let's see two reasons for being contested. The first one is the proof that Proclus directly suggests, and is this one. The quality of right angle is in fact manifest from our common notion. So Proclus said that common notion for people that is not expert are simply the action about equality and addition that you find in the postulate, something as equal, added to equal are equal, for example. What we could consider today as an axiom of identity and addition, okay? It's a little bit more complicated, but to go quicker, we can intend it in this way. So the quality of our angle is in fact manifest from a common notion that is in modern terms is a consequence of the obvious axiom of identity and addition. The mere relation that each of the two angles has with the limit of its indefinite increase and decrease makes the right ones equal. For this is how we have got the first right angle, by making equal each of the two angles that stand on each side of the right line they stand on. So this is a little bit obscure, so I try to give an explanation. Proclus' argument seems to be this one. Let a segment OA be given, lying on a straight line of you want on a right or a larger segment. Here you see, and then rotate OA around O, a right angle, better two right angles are got when the two angles are formed between O a prime and A become equal. Okay, this is the definition. By common notion, all halves of the whole domain of variation of all angles so obtained are equal, those all right angles are equals. So we have to note that for Euclid, angles are only angles smaller than the flat angles. A flat angle is not an angle, anything bigger than flat angle is not an angle. So the idea is that if I go from this position here to this position here, I have exhausted the range of variation of the angle that I can take, and so I have the same range of variation. In any case, the half of the same is always the same. This is the argument. So you have to assume continuity. Of course, there is always continuity on the continuity for Euclid is, so to say, something manifest from the fact that we're working on a plane that take it to be continuous. So there is no discussion about it. If you want another way, I can make a talk on Euclid geometry continuity. This is a completely other talk, but this is to take it for granted, of course. The argument has a chance to be plausible, if not valid, only if it is supposed that the domain of variation of all angles are equal, namely in modern terms, all flat angles are equal. Insofar as Euclid has no notion akin to that of a flat angle, this assumption corresponds in its setting to the assumption that all sums of two angles whose non-common sides are in a straight line are equal to one another. Faced to this definition of right angles, according to which when a straight line set up on a straight line makes the adjacent angle equal to one another, each of the equal angle is right, and the admission as a common notion that the halves of equal are equal, this statement is in fact equivalent to postulate 4. So Proclus' argument by common notion fails because it's based on a supposition that is equivalent to postulate itself. But so it's not a good proof. But this is an example of proof that have been presented as a proof, but that cannot be accepted. In this case, the proof is correct. That is a proof of A entails A. It's a proof that postulate 4 entails postulate 4. But obvious. And so not something strange. But implicitly suggests a postulate alternative to postulate 4, which is equally strong than postulate 4, which is apparently closer to Euclid's use of this last postulate in book 1, namely the sum of any pair of adjacent angles are equal, or perhaps even better, the sum of any pair of adjacent angles whose non-common sides are in a straight line are equal. This is apparently what really what is equivalent to postulate 4. Of course, if you use this postulate in place of postulate 4, we have to modify some proposition in the element, but the modification is only cosmetic, in fact. So we could imagine, and why I suggest that, not because I want to correct postulate 4, but I want to say that this postulate is in fact what is operative in the element. This is what he used. In fact, he explicitly mentioned postulate 4 only 2 times in the element, in the first book of the element, sorry. By the way, to be more precise, explicitly mention is not the good expression, because he explicitly mentioned nothing, Euclid. He never explicitly mentioned a postulate. What is normally mentioned, as in this case in square parentheses, are but the commentator. It is the commentator, it that makes the commentary. So what I say that is the only two places where postulate 4 is explicitly mentioned, I mean, in fact, the only 2 places where the reference of postulate 4 is absolutely evident. So evident that the commentator write clearly postulate 4, as in this case here. And so here what he say, then we have the straight line AB stand on the straight line CB, and the angle ABC and the angle ABE, so I prove by absurd. So you have to imagine that ABC and CBE are 2 right angles. So it's insofar they are 2 right angles, therefore the angle CBA AB are equal to the angle CBA ABD. So it of course cannot be the case. It is a contradiction. So what is taking is the sum of 2 right angles are equal, in fact. Remember, the figure is not clear because they prove by absurd, so the figure is wrong. But the idea is that CBA and CBE and ABE are 2 right angles by supposition. Okay? The contradiction. And the other case is the case of vertical angles. And here the proof is clear. What is the fact that is proved clear? Why the 2 vertical angles here are equal? Because what is equal are the angle AAD and DB are equal to 2 right angles, but the angle CEA and AED are also proved equal to the right angle, and therefore the angle CAAD are equal. So essentially the idea is this one. This angle is equal to this angle. Sorry. This angle here is equal to this angle here. So this is angle, of course. This angle here is equal to this angle here. Okay? So again, what is relevant here is that this flat angle is equal to this flat angle. That is that the sum of 2 right angles are equal. So in both cases, what really works is not that the right angles are equal, but what really works is the sum of 2 right angles are equal. So this could suggest that, in fact, Euclid should have probably given a postulate with the same reductive strength, but formulated in a little bit different way. Because what he used, in fact, is not the postulate, but are consequences of the postulate. That's what I did in the beginning. Okay, is up to here clear? But Proclus say, my argument by common notion is, however, not the only one to give a postulate for. He also provide what he call a proof by lines, apodexis Grammatican, sorry, I do not see. Here, so what means a proof by, what you call a proof by figure or by transposition. So what is the idea of this? This is the English translation of Proclus. The idea is that we take two right angle ABC and DEF and superpose one to the other. And if the superposition is okay, that DEF, when is superposed with DE superposed to AB, so we have also that EF is superposed to BC, that all is correct, and so the angle are equal. But suppose that is not the case, suppose that you superpose DE to AB, and EF does not superpose with BC, but is something as BG, and so it's easy to find the contradiction. Because this, you have this right angle, so this is equal to that, but also this is equal to that, and of course this cannot be. Okay, so this is the idea. In a modern term, superpose the angle BOC to the angle QUR with OC superposed to UR, and then the former smaller than the latter. Suppose then the former is smaller than the latter. You have this situation here, you have this equality, and of course you have that PUQ is smaller than PUQ. Okay, what you cannot do. Okay, so this is proof. So the fact that this proof is possible is very well known from the time of Proclus. But are these proofs admissible? So is the proof, well, the first one is wrong, simply. So it's not a question to be admissible. It's admissible, but it's wrong. It's a wrong admissible proof. Because it's a proof by a postulate that's equivalent to what you want to prove. So it's not a wrong proof, it's a good proof. But this proof does not prove what we want to prove. The other one is admissible? In a sense, certainly not. Since the method by superposition of angle is based on a rigid transportation of angle as such, which is no way licensed by Euclid linearity supposition, definition, postulate, and common notion. I will come back on this soon. Okay, so you see, the idea is that we take this and we transpose here. We take it and we transpose here, but this is something that is not a geometrical operation. It seems that it takes, in fact, not angle, but sort of pattern of angle, mechanical pattern of angle. And you take it and you transpose, but this is, of course, not what is admitted in Euclidean geometry. So in this sense, it is proved by transposition, by superposition, that Proclus give is not admissible. And so, and the fact that we can prove the postulate in this way, it was very known by Proclus, but before him by Geminus, but this is not a reason to make that postulate probable in Euclid, because it's probable by a method that is not a good method. But in another sense, the proof is obviously correct. Since the method by superposition is openly used twice in book 1 by Euclid himself, in the proof of proposition 1.4 and 1.8. So we are here in front of a very strange question that Hilbert spent a lot of time to reflect on. On one side, the method is not acceptable, clearly not acceptable. On the other side, the method is applied in the proof of two propositions.
Sorry, can you say again why it's clearly not admissible? I know that you explained it, but somehow I didn't quite understand.
What the question?
Why it's not like this? It's not
admissible.
Clearly, but I didn't understand what's clearly.
You have two right angles. Okay. What Euclid is probably suggesting to take this as superposition. And to say if there is something that goes this way, it's not good. But how can you do? You cannot take this angle and put here. You would have you need to have a method to place angle to do it.
Yes,
But the method to place angle depends on postulate 4.
I do it. I mean, I can do it. I do it in my mind, and you did it. You just did it. So
Yeah, but that's
No postulate.
but it's not. You can do empirically, but it's not admissible within the setting of using elements.
Yeah, but then there is a postulate implicit because you say yourself and you say, okay, now I understand what the conundrum is. Okay, thank you. So it's a bit
So
like
we're
complex.
not allowed to rotate.
If you rotate, you have two angles here. You can rotate this one. Not really, you cannot rotate, but you can construct something that's similar to a rotation. But this wouldn't say nothing about it. So if you want to compare this and this, you have to take this and to put here, or to have a theorem that tells you that I can construct here an angle congruent to this. And in fact, we have this method. This method of transposes angle is given by Euclid. And the idea is that how I can transpose this angle here, I take a triangle and then I transpose the triangle. But to prove that this method of translation of angles is good, depend on 1,4 and depend also on postulate 1,4 and proposition 1,4 and 1,8 that are proved by transposition. So the method of this operation of putting this angle here, better to construct here an angle congruent to that, this is permissible in Euclid. The point is not permissible at this stage, because the permissibility of this method depends on what you want to prove. That is the postulate 4 and the proposition 1,4 and 1,8. So circularity. Okay? Good. But the fact is 1,4 and 1,8, before proving the transposability of angle by this method, and the contrary, by giving a lemma for proving the transposability of angle, use this method. Here is proposition 1,4. For if the triangle ABC be applied to the triangle DEF, and if the point A be placed on the point D, and the straight line AB on DE, then the point B will also coincide with E, because AB is equal to DE. Again, AB coinciding with DE, the straight line AC will also coincide with DF, because the angle BAC is equal to the angle DEF. So what is the idea? By the way, proposition 1,4, I have to prove side angle side. Okay? Sorry, I did not say. We have two triangles, AB, C, D, E, F. This equal to this equal to this angle equal to this angle. So the idea is this segment is equal to this segment, this angle is equal to this angle, this angle is equal to that. This is what I have to do. So the idea is I take this point I put here. Then when I put this point here, this segment I put here. But insofar the segment is equal to this one, so the point E will arrive here. Then I take this segment that I put here. So insofar the angle is equal, when I put the segment here, it will also be on this straight line. And insofar it is equal, I will arrive here. So we have a point here. This point, there is only one segment. Insofar I have, this is exactly the one transposed here. This is equal because it was. Okay? Nice argument, but of course require the rigid transposition. We have to say that when we transpose the angles, I do not change them. And the only way that you can give something similar to transposition of angle is proposition 1, 2 that allow to transpose segment. 1 to tell if you have a point and a segment, you can construct on this point a segment is equal to this one. But unfortunately, when you make the application, the inclination of the segment with respect to this segment is fixed by the reciprocal position that you cannot choose. So when you transpose this here and this here, you completely destroy the angle. The angle is not concerned on the transposition. You could transpose one angle and the other into inclination that does not depend on the initial angle that they have, but depends on the partial relationship this point. Okay? So we have no rigid transposition. But Euclid supposes that there is rigid transposition in this argument. But if the argument is valid, so it's valid also the other argument by Proclus. So strange. And the same for 1/8. 1/8, if you can read it the same, 1/8 is side, side, side. So the idea is you have to triangle, you transpose this here, and then insofar the angular, all the angular equal, the right angle should be equal. Why? Because in 1/7 it has proved that you cannot have something like that where this is equal to this and this is equal to this. It cannot be. So the triangle on one side of a given segment, you can construct only one triangle. Or if you want, of 3 given sides, you can construct only 4 triangles that differ by symmetry. To here and to here. So if you take the symmetry fixed, you take only the side, and you take also the side, there is only one. So you cannot have. And so insofar as you approve 1/7, then by transposition, this on this, this on this, this on this, there is only one possible way, and so coincidence equal. But again, you have to take into transpose. So apparently, answer the question, why did Euclid use the method of superposition of angle to prove proposition 1/4 and 1/8, but did not the same to prove 1/4, postulate 4? Because if you accept this method, postulate 1/4 is obviously probable, as Proclus suggested. And the proof is so obvious that it is impossible to imagine that Euclid did not see this possibility. Because it's an obvious application of the same method on 1/4 and 1/8. Or in other terms, are there differences relevant enough between the use of this method by in Euclid own proof of postulate proposition 1/4 and 1/8 and the use it should be made of it to prove postulate 4 that make the former admissible and the latter not so from Euclid perspective? So there are some differences between the way we prove 1/4 and 1/8 and the way in which the method would be applied to prove a postulate that can suggest that it can accept one but not the other. The first difference is manifest as clear in material. In the former use, in the proof of the 1/8 and 1/4, what is transported are not angles but triangles. In the case of Proclus, you transport angles. But it's immaterial because, of course, when you have an angle here, you can, of course, trace this and then transport the angle. So the difference is purely cosmetic. The other difference, a second difference is also manifest between the use of method in proof 1/4 and the use in Proclus and my proof. In the former proof, the method is used within a direct proof. In the latter one is used within a proof by reduction, proof by absurd. As a consequence, the former proof, the method makes an angle completely superposed to another angle, determinately equal to it, while in the latter case, it makes an angle partially superposed to another angle provisionally supposed to be different from it. As relevant as this difference might be taken to be, and I think it is really different, is in fact, it is a fact that it disappears when the latter proof are compared with the proof of 1/8, because also the proof of 1/8 is by reduction. So there is a relevant difference between the proof of Proclus and the proof of 1/4, but there is no relevant difference between the proof of Proclus and the proof of 1/8. So it means that the same method is applied in 1/4 in a direct way and in 1/8 in a proof by reduction. So apparently Euclid admitted the proof in the both cases. I leave to the discussion to establish whether other relevant differences can be detected. I do not see them. In fact, we do not see them. It follows that the only possible reason that may have pushed Euclid to use the method to prove a 1/4 and 1/8, but not to prove a postulate 4, and rather to take the latter one as a liminary supposition, postulate 4, is the desire to avoid as much as possible the use of this questionable method. So things seem to appear to be this way. I do not want the method of superposition. But in the case of 1/4 and 1/8, I'm forced to take it. So I do not like it, but I have no other choice. So I take it. But I do not want to take it in a time. So I do not want to take it in the case of the postulate 4. So I do not make it. I make it as small as I can, as little as I can. If on the one side it is justify Euclid's admission of an evident stretch of his method to prove of proof to get a proof of this proposition, crucial proposition, one thing that is important to say, clear, absolutely clear for the professional, perhaps not for the student. 1/4 is angle side angle. 1/8 is side. These are crucial. Without this, you do not make geometry. So Euclid could not say, okay, I do not prove these two propositions. If without these two propositions, there is no Euclid geometry. Okay, so Euclid was forced to prove these two criteria of a congruence of triangle. He could not avoid to do that. And the point is, he could not prove using the postulate, so he made a bit of exception to his rigor to prove it in a not completely rigorous way. Good. But then, this idea of Euclid making a little stretch doesn't justify neither his renounce of doing the same proof of postulate 4. Why not to make exception also for postulate 4? Nor his decision of taking postulate 4 as a linear assumption and proposition 1/4 and 1/8 as theorem to be proved, rather than taking at least a part of them as a linear assumption too. So he did not want to use this method. He could have taken 1/4 as a postulate. Why did not do it? That is, by the way, what the Euclid Hilbert does. He take a part of 1/4 as a postulate. By the way, in the Hilbert setting, when you take a part of 1/4, then you can prove the other part of 1/4 also 8. In the case of Euclid, it's not so evident whether you can take only one of the two and not two, because the setting of Hilbert and Euclid is not exactly the same. So we have no definitive argument about that, but possibly Victor, he could have. I don't think that we can take, Euclid could have taken only one of the two as a postulate. Possibly he would have needed to take both of them. But this is not something that I am sure about. We try to understand it, but we do not arrive to a complete conclusion. So this is the first conundrum, or only the first one. The question is why he act in two different ways with proposition 1/4 and 1/8 and in postulate 4. Why? The idea that you want to limit as much as possible the method of superposition is not a good answer, of course. Now, becoming to the other or more serious conundrum, it is, however, in order to come back to the method of by superposition and the proof of 1/4 and 1/8. Now I will go very, very quick on this, because in the history of mathematics, there is an example by a paper of 83 by Robert Wagner, Euclid intended interpretation of superposition, in which Robert Wagner, there is a nice fact here, the paper Robert Wagner has been suggested to me, but Wagner signs. Robert Wagner is the second name, Wagner signs, Wagner is the first name, and so I was Wagner signs in that board explaining the idea of Robert Wagner. Said, but Wagner, you know, it's not me. My name is my first name Wagner. This is the last name Wagner. Okay, this is not really so important. So I did not know the paper of Robert Wagner, but my good friend, the friend of Giselle or many other of you, in fact, yes, and of John, attracted my attention to this nice but wrong paper of Robert Wagner. What is the idea of Robert Wagner? I would not enter because it takes a lot of time. The idea of Robert Wagner is essential to say it very, very quickly, that it is what we call a superposition. It could be intended, in fact, as abstraction. So the basic idea is that you have two triangles here, and then you construct a triangle, a triangle with the same side here. Here, you reconstruct this triangle here, so and you reconstruct the same triangle on itself. Okay? To take this triangle and to reconstruct once on this one and once on itself. And insofar as this, Robert Wagner say, insofar as the algorithm to construct the two, one on it and one on itself is the same algorithm, it should give the same result. And so, insofar as the two triangles coincide, one with this and one with this, should be equal, but insofar they should also be equal because they result from the same algorithm, we have two propositions. 1, 4, 1, 8. The argument is wrong. For different reasons, I do not would enter 2. I would say something definitive on the fact that is wrong. Essentially, I do not enter in many details. There is a circularity because the fact that the algorithm that suggested by Robert Panza work depend on 1, 4, and 1, 8. So the argument is correct. Wagner argument is totally correct, but it's totally correct in 4, so 1, 4, 1, 8. That is exactly what you have to prove. Okay. Now, the fact that the argument is not correct is also proven in a definitive way by Cosette. They constructed a model of the 5 postulate and the 5 common notion of the element, in which all is the model, so all the postulate holds and all the common notion holds, but 1, 4 does not hold and 1, 8 does not hold. So this is definitive proof on the fact that we cannot prove a 1, 4, and 1, 8 from the postulates. And so we need to add it as an axiom or something like it as an axiom. That is, by the way, something that Hilbert already arrived to this conclusion because this is what he did. But to the best of our knowledge, Hilbert did not give a meta-theoretic proof of the fact that he could not have proved postulate proposition 1, 4, and 1, 8 starting from the axiom. The model of Jose, we will write a paper on that, prove definitely that Robert Wagner cannot be wrong, could not be right. Cannot be right because of mathematical reason. Then we can discuss where is the error. The error, according to Jose and me, we agree on that, is essentially a question of circularity. Okay, this is the method of Wagner. I do not enter in all the detail because I see that I took a lot of time, but okay. Okay, this is also variant method. Now, so this excursus with Robert Wagner is to say that no, the proof by transposition, the superposition, they're not good proofs. They are not good proofs, but they are proof the Euclid is method that Euclid used. This is the first point. Simply that Euclid add something implicitly to his postulates, that is the method by superposition. But use it only to prove 1, 4, and 1, 8, but not to prove postulate 4. Why? First conundrum. Now, second conundrum. It appears that when we observe that once it has been proved, proposition 1, 8 to provide a safe method for transporting angles together. No, this is an error in English, but what I want to say is the following. Suppose that you have proved 1, 8. No problem as you do it. Suppose that you have proven in a good way. Suppose you have proven in a bad way. Suppose that you take it as a postulate. No problem. You have 1, 8. 1, 8 tell you side. Okay. So now,
Marco, we cannot see the board. Can you move the camera to the board you're using? Thank you.
okay. Okay.
It's in the board.
Okay, sorry. So what is the idea of 1, 8? 1, 8 is, I explain here in this figure, let it be required to transport the angle A of B on the segment CD. Okay? 1, 8 give a method to do it. Why? Because you trace the segment AB. Okay? You have the angle I of B, so segment AB. And now you have a triangle. Then by 1, 2, transport OB in C as CB prime. CB prime, in fact, is a segment equal to OB that is constructed by the method of 1, 2 on the point O. You see that the inclination is the one that results from a Euclid construction. So it's not my choice. You apply the construction, This is our, in fact, you have two choices because you have to construct an equilateral triangle. You can construct on a side or another side to, in fact, it's this inclination of another symmetric inclination, but you cannot choose the inclination. You can choose one or the other. So this is one of them. And so you have this one. Then by 1, 3, transport CB prime on CD. What is 1, 3? 1, 3 say you have two segments and you can put one on the other by a circle. So you trace the circle and then the point intersection. Of course, you have rotated a circle, essentially speaking. Now by 1, 2, transport OA in C again as no, by 1, 2, transport OA, that is this one, now, in C as A, C a prime. Again, the inclination, the one that is given. And by 1, 2, transport AB in B, AB in B second here as B2 S2. So now you have the three segment. One is CB prime is equal to B, one CA prime is equal to AO, and the other is BS2 that is equal to AB. And then you can start to use the circle and you take the intersection. So far you have side, side, side. This triangle is the same or the other because they are the same size. So the essential idea is to transport the segment to the lights independently one to the other, and then you reconstruct the triangle by circle, intersection of circle, and insofar you have 1/8 is side, 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 the two triangles are obviously equal, and so the angle is equal. So in fact you have transported an angle. Okay? It's clear? Because now the triangle that you see here, CA3, B3, is by side, a congruent to AOB, and so the angle in C is equal to the angle in O. It's exactly what you wanted. Okay? So you have a method to transport angle in Euclid element, but this method requires 1/8. That requires 1/4. Okay? But it does not require postulate 4. This method does not require postulate 4. So another conundrum is the following. Using the transportation of angle, we should now be able to prove postulate 4 by repeating mutatis mutandis, Proclus or my previous proof. It is, however, a fact not only that Euclid does not do it, but also that it does not consider proposition 1/4 and 1/8 still enough to allow him to solve the transposition of angle problem, namely to provide the previous method to transpose angle. Here you see, we use nothing than 1, 2, 1, 8. So we simply take one segment, we put another segment, then we take a circle in the point of intersection. So there is no use of postulate 4 here. So question is, why Euclid does not give the method of transportation of angle that it is apparently an immediate consequence of 1/8 as a proposition 1/9? Why the element does not present a proposition 1/9 that tell you, given an angle, construct an angle congruent to it on a given segment? Apparently, it could have done it, but it does not. It does not. And not only, apparently, it could have done it, and it could use this method of transposition of angle, justified by 1/8, not to prove 1/8 or 1/4, as Wagner suggests. This would be circular, but to prove postulate 4. Now, without superposition. So why it did not do it? Euclid does an implicit answer to this question. Because he gives this method of transposition of angle, but he gives this method only in proposition 123, which is, of course, a problem and follows proposition 122. So the point is that he does not prove this method in proposition 19, but he prove in proposition 123 and make it depend on proposition 122. What proposition 122 says, it says from three segments that are equal to three given segments, construct a triangle. And then 123 on a given segment from a point on it construct a rectilinear angle equal to a given rectilinear angle. Except of some aspect that seem irrelevant, here Euclid's solution of this proposition is exactly the first one that I gave. Now I can to construct a triangle with three segments and then I can transpose. But to solve proposition one, I gave the method, but it's essentially what I said. At first glance, this construction seems only to require 1, 2, 1, 3, 1, 4, and 1, 8, sorry, as its precondition. Hence the question, why Euclid wait so long to solve this problem? So why Euclid does not give this method of transposition of angle as proposition 1, 9, and why does not use it to prove postulate 4? Why does not rely on their solution to prove postulate 4? The answer comes from proposition 120, together with the part of the statement of proposition 122 that I have omitted in my previous quote. 122, see here, I made an omission here, ellipsis. If you read that is ellipsis here, you find the solution. Here what is saying proposition 120. In all triangles, two sides of every interchanged among the three one are greater than the remaining one. So all the sides of a triangle satisfy the triangular inequality in modern terms. And in proof in 22, it is needed that the segment of every interchange be greater than the remaining one, since in the same way, two sides of a triangle of every interchange are greater than the remaining one. In other terms, Euclid is apparently not interested in stating any sufficient condition for construction of a triangle, but is interested in stating a necessary condition. He says a triangle cannot be constructed by three segments whatsoever. In order to be able to construct a triangle, you need to have two segments that satisfy the triangular inequality. The sum of two is smaller than the other. And so it is that he proved in the meantime, between 1/8 and 122, he proved the triangular inequality. And to prove the triangular inequality, he used postulate 1,4. And so it is apparently the reason for which he does not use the method of transposition of angle given by 1/8 to prove postulate 4, because he considered that he cannot prove this transposition of angle without having a necessary condition for construction of triangle, and to prove the necessary condition for constructing a triangle, he used postulate 1,4. Necessary condition. This is quite strange because we would expect that it requires a sufficient condition. A necessary condition, why is so fundamental? So it seems to consider that 120 ensure at the same time that a triangle is constructible from three segments only if they meet the triangular condition, and that the three segments equal to the side of a given triangle meet the triangular condition. Together with the admission already made along the solution proposition 1,1 that the triangle is constructible from three segments if they meet the triangular condition, so the sufficient condition that is taken for granted already in the proof of 1,1, and with the solution 1,2, we have a necessary and sufficient condition for allowing the solution of proposition 123. So Euclid's point seems that the proposition 123 requires the proof of 120, namely of a necessary condition for the solution 122. But the proof of 120 appears in cascade to the proof of 119. In all triangle, an angle greater than another is subtended by a side greater than the side that subtended is last angle. 118, in cascade, in all triangle, a side greater than another side subtend an angle greater than the angle subtended by this last side. 116, in all triangle, external angle are greater than internal angle. And finally, 115 vertical angle are equal. But 115 is the example that I gave in application of postulate 4. So 115 requires postulate 4. So insofar as this is proved in cascade, we need 115 to prove all the other, and to prove 115, we need postulate 4. So according to Euclid, it seems that Euclid did not use the method of transposition of angle given by proposition 8 to prove postulate 4, because Euclid felt that it would not have been legitimated to use this method without having proved a necessary condition for computation of angle, and postulate 4 is used to give them this necessary condition. Good. This does not close the question, however, because this attitude of Euclid is very strange. Because the partisan of the pursuit of proof postulate 4 have at least 3 options open. There are 3 ways in which we can criticize Euclid. We can first reject the idea that the solution of the transposition of angle problem requires the proof of a necessary condition for the construction of triangle from 3 given segments. We can say, but Euclid, we do not need a necessary condition. Because what we want to do is that we have a triangle. We have to construct another triangle with the same sides. So if the side here allow to construct a triangle, of course they allow to construct a triangle here, because already here they construct a triangle. So we don't know why they allow to construct a triangle here. But what we do, we know that they allow to construct a triangle. So why they should not allow to construct another triangle if they allow to construct already a triangle? So this can be. We do not need this because it's implicit that we can do it. I will make an objection to this argument against Euclid. So do not take it as correct. But we can imagine someone that makes this argument. Second, you can look for an alternative proof of 120 that does not indirectly appeal to postulate 4. This, the proof of Euclid use postulate 4 to prove 120. We can imagine, okay, we agree with you, Euclid, we need a necessary condition. But we can prove the necessary condition without using postulate 14. And this is exactly what we will do. Third, we can look for an alternative proof of 115 that does not appeal to postulate 4. To go for the first option, the one that Ahmed did not like because he made a no with his head, one may argue that the very fact that a triangle is given is enough to ensure that another triangle is constructible on 3 segments equal to its side. But against that, a partisan of Euclid's attitude should argue that taking this for granted goes dangerously close to inadmissible supposition, namely the transposition of segment by 1, 2 conserve their constructive properties. That is something similar to isotropy of space, which in the present case, one may also state more specifically in this way, what is constructed out of some given segment is also constructible out of as many segments equal to them. So it seems that Euclid does not follow one, so it requires a necessary condition because it does not accept that what is constructible here with 3 segments is also constructible here with the same segment. That is that the property of constructibility are maintained by superposition, by transposition by 1, 2. And this is a very subtle attitude because in some sense, you could say Euclid does not want to take isotropy as accepted, admitted. But what remains, and Euclid seems to accept it in other cases. That is, but okay, we can say we did not go by this solution because we can say Euclid could have had a reason for not doing that. But it remains that in other cases, it seems not really sensible to this argument. Now, going for solution 2, looking for, no, I said that we would have to do 2, but in fact we did 3. Looking for an alternative solution 120 that does not indirectly appeal to 14. What is 120? 120 is the fact that the side of a triangle satisfies the triangular condition. So the idea, but this is quite easy to prove. Why? Because we have a segment here, we have a triangle here, so we take a circle here, and in the end of the story, what we have to prove is the 2 circles that meet in a point do not meet interior to the triangle again. They meet the other point of intersection is outside of the triangle. So you can say this is obvious. No, it's not obvious because this is exactly what 120 proof. So we cannot, if we hope to use this, how evident can appear from an intuitive point of view, this is exactly the content of 120. So to hope that we can prove 120 without using, I don't know what is that, this one. I cannot answer. It's my son. Is in fact supposed that we take another axiom that is a very famous axiom, that is a straight line is the shorter path between 2 points. Of course, if we have this other axiom, that's easy. Of course, the triangular inequality is easy. But Euclid has not this other axiom. By the way, not only has not this other axiom, but is even not a metric. John, can you see whether the problem is a problem with my son, but John knows him very well, so he can answer if there is some problem. Okay, good. So I think that this idea cannot work because it would require, it would introduce a little circularity or would require a supplementary action that is a metric action, by the way. Not only is an action that Euclid does not give, but is an action in the style that Euclid does not use. That is a metric action. It remains option 3. The main point that I want to do today, that we want to do today, is that option 3 is correct. We can go. And it's based on an alternative proof of 115. A proof of 115 that does not use postulate 4. So I remember you the proof of 115 that Euclid gave himself. The proof of 115 that Euclid gave himself is here. Okay. What? No, it's not this one. It's this. Yes, it's this one. Let me make it a little bit bigger because I read nothing myself. Okay. I say that the angle AEC is equal to the angle DEB. You could have said also that the angle AED is equal to the angle ACB, would have been more, but this is what it proves. So vertical angle, two vertical angle are equal. And the angle CEB to the angle AED. For since the straight line AE stand on the straight line CD, making the angle CEA and AED, the angle, the sum of this angle is equal to 2 right angle. This is something that is proven in Proposition 113. Quite easy to prove, so not problematic. I do not give the proof. Okay, again, since the straight line DE stand on the straight line AB, DE on AB, making these 2 angles, the angle DED and DEB are equal to 2 right angles, exactly for the same reason than before. And so, but the angle CEA and AED were also proved equal to 2 right angles. And therefore, the angle CEA, AED are equal to the angle AED and DBD, because in fact, this angle here is equal to this angle here, as insofar this is common. It's clear the point, okay? But this requires that 2 flat angles are equal. And 2 flat angles are equal in Euclid parlance is simply the sum of 2 right angles are equal. And to have the sum of 2 right angles equal, we need to know either a postulate to say that the sum of 2 right angles is equal, or a postulate to say that right angle is equal. So the sum of equal are equal. So this is a use postulate 1.4. So is there a way to prove vertical angles without postulate 4? Yes, is there. The proof is Jose suggested this proof. We can say, if I want to be a little bit antipathic with Jose, that the proof is also suggested by Ashton, not directly, but there is some hint of the proof in Ashton. Here is. So this is the situation. We have the two vertical angles. Beyond Euclid.
No, it is the upgrade. No,
It's a book by Springer, Euclid and Beyond.
no, but
Euclid
it is
and-
the upgrade.
Yeah, it's not an upgrade.
It's a fantastic book, really fantastic. So what we require is something that it could be a little bit problematic, but it's something that Euclid himself required in the proof of 1-3. It is that if we have two segments, we can choose what is the smaller one. Okay? If we can choose the smaller one between two segments, we are, of course, also able to choose the smaller one between 4 segments. Okay? Notice that if supposing that we cannot choose the smaller one is not really a problem of our proof, simply the proof divide in 8. I don't know, 2 power 3, I think, 8 different cases. But the proof is simply a little bit more confused about the same. Okay, so suppose that we can choose the smaller segment between the 4 segments you see here, and the smaller segment is OC. Now we center O and radius OEC, trace the circle, and so we have that OC is equal to O A prime, O D prime, or OB prime, by construction of circle. Okay, let me take a little bit smaller. Okay, so now we have that A prime O is equal to OC, because they are already on the same circle. And now we know that the angle A prime, the angle here, is equal to the angle here because they are isosceles triangles, proposition 1-5. Okay? And now we know that A prime B prime, that is the diameter of the circle, is equal to C D prime, the other triangle diameter of the circle, because they are sum of 2 radius and the radius are equal. And so we have this T triangle here, this one, A prime C D prime, and this one, C A prime B prime. You see the 2 triangles? This one and this one. Okay? This one and this one. Now, this one are equal by 1/4, because this is common. This is equal to this one, and the angle is equal because the angle is also a triangle. And so O prime O is equal on CO, because they are radius. D O prime is equal to B prime O prime, and that is equal to this one. So this segment here is equal to this segment here. This segment here is equal to this segment here. And what we already proved, that this segment here is equal to this segment here. So by 1/8, the triangle is equal. And so this angle here is equal to this angle here. We can, in the other, applying the same reasoning, we shall also prove on the other side that that is equal to that. So it is required no postulate 4, and it is required nothing else than 1/5, 1/4, and 1/8. But now that we have 1/15, we can follow Euclid, because in the proof of 1/17, 16, 18, 19, there is no reference to postulate 4. And so we arrive, but this is what Euclid does. So trust me, there is no reference to postulate 1/4. And so we arrive to 120, exactly as Euclid. But simply now we are arrived to 120 without using postulate 1/4. Because the only use of postulate 1/4 that is done is in this. Oh, remember, you use postulate 1.4 also in 1.14, but 1.14 does not enter the chain on argument. So we can forget that is use of 1.4. Okay, we can forget proposition 1.14 and simply prove 1.14 in the end of this chain or argument when we approve postulate 1.4. And so now we can prove 120, 122, 123. And now we have the method of superposition of transposition of angle. And now we can repeat a Proclus proof, but this time not by superposition, but by transposition of angle, made possible by proposition 123, that now is proved exactly like you could want under after having proven necessary condition for construction of angles. So we changed nothing in Euclid, and we simply transformed a little bit the proof of 115. But this a little bit transposition, little bit correction, in fact, is not really very local. Why is not really very local? Is a problem? Why is not really very local? It's not really very local, but I hope that she does not go into. Okay. Sorry?
She's getting some water. She's so excited she's thirsty. Super knowledge and
Okay.
hydration. Right. They come together.
Okay. Now this transposing modification is not so local, in fact, because what we have to do is not only to change the proof of 115, but also to change the order on the proof of some proposition. We can invert the order. So we cannot simply say something that is very often said, okay, Euclid does not prove postulate 1.4 because postulate 4 in fact is interpolated. And in fact, someone else introduced it. Euclid, in fact, did not have it, so this is the reason for which it did not prove. So then someone else that did not understand the argument of Euclid introduced it, but in fact, Euclid did not prove it because the proof is so trivial that Euclid cannot prove anything that he used, because a lot of things that Euclid used, he did not prove. This is true, but simply obviously probable. And Euclid does not prove for the simple reason Euclid is a mathematician. And in mathematician does not prove any lemma or theorem. So the lemma that are trivial, he read to the reader to prove. So we cannot reason this way, because if this were the fact, Euclid possibly he would have not have given postulate 1.4, and possibly postulate 1.4 is interpolated, and possibly Euclid could have considered 1.4 as obviously probable and simply did not make the proof explicitly because he considered it simple. But he would have given the proposition in another order, the order that he gives, because otherwise he could not do that. So here the changes that requested is a little bit too much. And so the only thing that we can imagine simply Euclid did not see this possibility of proving postulate 1.4 without using 115. Sorry, this way of proving 115 without using postulate 1.4. Now that we have that, I can reconstruct the proof of Proclus in a much more detailed way. If you want, I can do it. Now this is the official proof that we suggest for postulate 1.4, and is much more. And this is, by the way, suggested by Hilbert, because this is the way in which Hilbert proved postulate 1.4. Hilbert proved it in this way. But remember, Euclid proved it using 1.4 as a proposition. So we have the two angles here, and both right angle. And so you suppose that we construct the triangle here, ABC, on these two rectangles, and then we have that, and then we transpose the triangle ABC here. Okay? And then when we transpose the triangle ABC here using 1/8, we can have two cases. Either the transpose of B is on UQ, and so we approve the postulate, or is not on UQ, so you see that here is in B3, and then contradiction. Okay? So if it is on UQ, we approve the postulate, all is okay. If it's not contradiction, it should be on UQ, so it's UQ, we approve the postulate 1.4. And this is exactly the proof of Proclus, but made in a little bit more precise and unquestionable way. So at this point, I'm practically finished. The question becomes very urgent. Why did Euclid choose to admit postulate 4 as a postulate? The question is relevant since, in the light of what I have just shown, it becomes clear that dissolving it by merely guessing the postulate 4 is in fact interpolated would require much more than merely omitting it from book 1 and supposing that Euclid did not prove it explicitly, since it took it as so obviously probable to make it unnecessary to actually prove it. He would also require to deeply change the order of a larger set of propositions of book 1 and the proof of some of them. As unbelievable as it might appear, the most plausible conclusion seemed then that Euclid simply did not see the possibility of avoiding postulate 4 by such a non-trivial modification of a relevant fragment of book 1. Thank you. Okay. Questions?
I'm sorry, I'm just a physics person, but how would we know? Does Gödel's theorem, could it possibly apply to this kind of stuff where we wouldn't be able to prove something that's so basic for the theories? Gödel's theorem, right?
Good.
Right.
Yeah.
Would we know if we hit a Gödel theorem wall?
No, I don't see any possible relation with
No?
the Gödel theorem. No. No, I don't know. Philosopher of mathematics is very fantasist, and they see Gödel theorem everywhere. I am one of those that think that the use of Gödel theorem is not so ubiquitous of generally people says, but in general, I don't see really how we could apply Gödel theorem here.
This is John. I think.
Gödel theory by the 2L1 thing require that we need a system in which we can make at least a Robinson arithmetic. And it is a system, I don't think, no, I don't see. I don't know whether Victor has something to say about that, but I don't see a possible relation.
I see it the same way as you do. Gödel has nothing to say about geometry. Geometry is decidable and complete if you extend it. So it's a phenomenon, as you said, of arithmetic, not of geometry.
So there is no connection here. But remember, I want to make one point clear. I hope that it was clear already, but I want to make it clear. I am not asking that Euclid could have proved postulate 4 in an appropriate way. I say that if we accept postulate provision 1.4 and 1.8, as he did, he could have proved postulate 1.4. So postulate 4 is a consequence of his postulate plus 1.4 and 1.8. Insofar as prove 1.4 and 1.8, it's a method that is not admissible, but he applied, then he could have proved postulate 1.8. And what is relevant in this reconstruction is not only that he could have proved postulate 1.8 by the same method used to prove postulate 1.4, proposition 1.4 and proposition 1.8, is that once he had proposition 1.4 and 1.8, he could have proved postulate 4 by a very admissible method. A totally admissible Euclidean method. Okay, Peter.
So are you suggesting that 1.4 and 1.8 should have been postulates of Euclid?
This is not what I suggest. This is what Hilbert suggests. Mutatis mutandis, because the setting of Hilbert is not the same setting of Euclid. There is a lot of difference. The most macroscopic one is Hilbert are not circles, and the other very macroscopic one is that the setting of Euclid is constructive, the setting of Hilbert is existential. So the settings are not equivalent. But if we identify a relation, we emerge one setting and another setting, it seems that what Hilbert is suggesting is that he cannot prove a postulate 1-4 at the point that you use a weaker statement of postulate 1-4 as a axiom. And in his setting, this weaker form of postulate 1-4 allows to prove postulate 1-8 in his setting, but not in Euclid setting. Because Hilbert assumed transportation of angle. So Hilbert assumed that if you have an angle and a straight line, you can construct, and a point on a straight line, you can construct on this point a straight line, and you can construct. There is an angle equal to the given angle on any point even in straight line. So you have an angle here, you have a straight line here, and a point here. One of the axioms of Euclid is that there is an angle here that is congruent to this angle here. So when once you rephrase it in Hilbert set in Euclid setting, this is transportation of angle.
You said, sorry.
Yeah, I was asking about program. I'm asking what your claim that postulate 4 can be proved. It's not that postulate 1, 2, and 3 are.
No.
Postulate 4. It's that postulate 1, 2, and 3 plus 1, 4, and 1, 8.
Of course.
As a new system of
course.
Can then be used to do this.
If you want, we can read it in this way. So this is not what explicitly suggested, but this is not historically very, it would be a strange assertion, but mathematically speaking, it is it. So we suggest that a system of postulates made by 1, 2, 3, 5, of course, this is necessary to a lot of things. No, we are not speaking of 5. All what they say here is independent of 5. Right? All this is given before that they use postulate 5. So this is in absolute geometry. We are in absolute geometry. All what I said, perhaps I should have said before, is in absolute geometry, not in Euclidean geometry. Okay, so postulate 5 is of course necessary to making Euclidean geometry, and not to distinguish absolute from Euclidean geometry, of course. But so if we take absolute geometry, we forget postulate 5. What we have proved is that we could have a system of axiom given 1, 2, 3 plus proposition 1-4 and proposition 1-8, and this would be a good axiomatic basis or postulating basis for absolute geometry that does not depend on transposition of angle. Yes. On transposition, does not depend on superposition, sorry.
I mean, there are some questions. For me, 1-8 seems like a plausible possibility. Side by side seems quite possible. But side angle side, I'm not so obviously convinced that this is true.
Well, it depends. When Hilbert considers something like, for example, like an action, and then you could go.
Yeah, but Marco said that's a very good system.
Very
Different flavor. Well, I think that's also an interesting question. For independent.
This is a question that we want to study, but we did not. I don't know whether Victor has a solution. Is 4 independent of 8? Did you study this?
If what is the question? If 4 is independent,
Proposition 4, no, proposition 8, or vice versa, is independent of proposition 4. So we can imagine
no, it is
proposition
dependent.
8
But,
given proposition 4 without a superposition.
yeah, as you pointed out, it is dependent, but the question is in what system? We know that in Euclid it is independent. We know it is dependent. We know that Tarski goes about this 5-segment axiom, which is some form of side angle side, but there are no angles. So in most places, you don't need both of them. You just can get one without the other.
Okay, but in Hilbert, for example, you need only one. But in a Euclid setting, apparently,
that's the question. You need to formalize Euclid and then to figure out. So you have
okay, exactly what we are doing.
Exactly.
But what I'm saying is still we do not have an answer to this question.
Not true that in Hilbert you only need one. In Hilbert you need 1/4 side angle side and transportation of angles.
But that's incongruence action, so yeah.
But it's not a complete,
Expectation of possibility of constructing work with over time.
but it is not, it's possibility of concept to have something angle, but it is an axiom.
Yeah, but because of, because it comes with, forms like Hilbert ordinance, like congruence with over.
Yeah.
So you have to constrain segmented angles, you have to be able to do that. Hilbert drum.
Can we make a little bit of order? No, I do not want you to stop to discuss. We want to discuss with all of us, not only between you.
Yeah.
So Adrian, what's your thought?
Okay,
I
no,
said it, so yeah.
okay, yeah, my point is that Hilbert proves 1/8 from 1/4,
Yes.
but he uses the fact that you can transport angles. And Euclid doesn't know that until a very until proposition 123, which that is proven in terms of other propositions and other propositions. So it is not true that 1/4 is enough for.
Okay, so it means that in the proof of Euclid of proposition 1/8, enter a reference to proposition 1/4, but it enter a reference to proposition 1/4 plus superposition.
Not only the transportation of angles.
We by superposition. Yeah.
Hilbert's does.
Okay. Other questions? John.
Go back to the argument. You had an argument at the very end against proposition for being an interpretation.
Let me see how I can share. Where is my? I close it. It should not. Is not closed. So this is the reason for which. So share. Yeah. So what do you want to go here?
Yeah, the argument and process. Is at the very, very end.
This one.
I suppose, is that the lesson?
I don't know what you want. Interpolated means simply that it was not in the original version of the element. So, what we call the elements today is, of course, not the book that Euclid published in his time, because Euclid published nothing. So what we call today the element is a reconstruction of the Euclid text by Heiberg, made in the end of 19th century. This reconstruction is based on a critical consideration of a lot of manuscripts and the stems that this manuscript came from, but it's still a guess. Okay, so someone can say that something that Heiberg put in the text, in fact, was not original, but was added after. Okay, so in technical terms, this means that it's interpolated. So 1/4 is interpolated, mean when Euclid used the element in a given class of geometry in Alexandra, it did not use postulate 4, but some commentators say, oh my God, there is something that is missing here. He used postulate 1/4.
Is this a conjecture?
But this is a conjecture that is made by many. I myself made this conjecture in a paper. Now I have not the same idea. Vincenzo De Risi made this conjecture. This is many people that made this conjecture.
Just for example, the 4 and 5 are interpreted. You could only have here's the reason. That's an example of such.
Yes, for example, yes, there are a notion, common notion, is the common opinion of the scholars is that the common opinion of the scholar is in fact that only 3 common notion are original, the other 2 are interpolated. So it would not be a scandal that postulate 4 is interpolated. Could not be a scandal. But this argument shows that apparently it's not.
What is the argument?
Sorry?
And just the argument you presented.
What I want to say that what is this the guess that 1/4 is interpolated? the picture that I have always imagined, and also Vincenzo there is imagining, but Vincenzo is much more prudent than me. And so Vincenzo does not explicitly say, but suggests that is interpolated, but he does not explicitly say it, because he considers that the pro and the contra of that. But the things is the following. Of course, postulate 1,4, you can prove it. The proof is by using the superposition as 1,418. And once you have 1,418, it's obvious how to prove it. So Euclid does not prove it because it's obvious that it could have proved. So it is not loses time to proving something that is so evident. It's so evident, provable by the same method that you already give. So it simply does not list it as the postulate. As insofar in Euclid, there is no explicit reference to the postulate. The explicit reference is added by the commentator. This does not appear to be any error. Then a commentator arrives, oh my God, but here is implicitly taken the quality of right angle, and did not prove it. So I put it as a postulate, so I solved the problem. And the commentator simply did not see that the postulate 1,4 is trivially probable. So this is the imagine. So we can admit that this is the case, but in this case, we should admit that the proof of 1,4 that Euclid has in mind dependent of superposition. Okay? And this is okay, that could be. But if we want that 1,4 be provable without superposition, so we need much more than simply omitting 1,4 and taking it as probable. We need to change other things, right? To change the proof of 115, also to change the order of propositions. Okay? So this is the argument. Of course, this is not a definitive argument against the fact it's interpolated. It simply says that the suggestion is interpolated is much less anodyne than apparently it may be.
Specifically, the form of postulate 4. I mean, postulate 4 is only, as it's used in book 1, it's not so much that the right angles are equal, but that a straight line has a constant measure, right? And that strikes me as more obvious.
This is, John, this is what I suggested in the beginning of the talk, that in fact what you use is not the fact that right angle is equal, but you use that if one angle is so we have two angles, and two sides, opposite side of the angle are in a right line, so right. The sum of these two angles is two right angles. So this is what you use, in fact.
Sure. Right.
So what you say is strange that they give another form, because what you use is that, is not the other. So it should have given as, but the point is another one. But John, also this requires a change, because if this would have been a postulate, proposition 113 would be unsensical. Because proposition 113 say that you have a segment and another segment of the segment, the sum of two angles is equal to two right. So this would be already the postulate. So why to prove, to take a postulate, or why to prove the postulate another time? Because this 113 is essentially this one.
All right, so 113 says two right angles.
Saying that the sum of these two is equal to right angle. And then it is also a strange thing that
that Euclid is thinking that all flat angles are equal. But he doesn't want to speak about flat angles because an angle is going to be of one segment over another. And if there are collinear, there is no inclination. So you cannot speak about it. How do you speak about flat angles? When you divide it into equal angles and you speak about the right angles, and then you say,
so this is the idea.
Then you have the right angles, therefore, every time that you have two of them, they're going to be
But,
equal to any time you have two of them.
by the way, Jose, I don't know whether you give me the permission to tell to our friends one of the conclusions that we are writing the last day of our work. It is a question of using right angle instead of flat angles is much more subtle than what it appears in first place, because what Euclid is doing here is cannot speak of a flat angle. So instead of flat angles, take the sum of two right angles. But the sum of two right angles is not an angle, because the sum of two right angles is a flat angle, but the flat angle is not an angle. So it means that Euclid is in fact using sum of angle as something else at angles. but something else that in fact is comparable by an order relation between angles. So we can say whether this angle is smaller or greater than the sum of two right angles. And we can also say that the sum of two angles, the less that one flat angle is smaller than a sum of two right angles. So using in fact two sort of types, one types for angle and one types for sum of angles. So the sum of two angles is not an angles. But also clear because the object of Euclid, the Euclid object Euclid are constructible. Given an angle, you can construct another angle. If you have two angles here, you can say that this angle is equal to the sum. But there are a lot of other angles that are equal to the sum. So the sum of two angles is not constructively determinated. Okay, so it's a purely quantitative notion. It's not a geometrical notion. It has no position. But you have something that is not an angle, but is congruent with an angle, and can be smaller than an angle, and can be greater. No, smaller, no. In the case of two right angles, but can be smaller than greater than an angle. It is congruent with a. Well, what I want to say, it appears that Euclid is dealing with two different sorts of objects, angle and sum of angles. And that these belong to different types, but these different types are, with some restriction, comparable under order. Sorry?
One is definable in terms of the other.
One is definable in terms of the other, yes, but under a construction that give only one particular model of the sum. I want to say, I take one angle, I take another angle, I can construct an angle that is equal to the sum of these two angles. But it's not the only angle that is equal to the sum of these two angles. We can also other angles. So the sum of two angles is not a definite object that you construct. It's a magnitude that can be exemplified by different construction. Okay? So it's essentially non-constructive. Of course, it's constructive in a sense, but it's constructible only insofar you can construct something that is congruent with.
Why is this distinction important? I understand the distinction that you have.
Why this distinction is important with respect to what I said today? Not important at all. In fact, I did not.
Yeah, so what? This is the language.
No.
And we're trying to be
It's awkward to say that the flat angle is not an angle. You can say that, but I would consider it a mistake.
No.
It makes the language artificially more difficult than it has to be.
No, Alex, now I don't know whether you give me the permission to get completely outside of the subject because it is another subject. But I think that is I was very happy that we discovered it in working because this changed completely my understanding of Euclid elements and it seemed to me that is very relevant, but has nothing to do with the talk of today. Yeah? I make it clear. The point is the following. I always suspected, but I'm the only one that is suspected that, for example, Radial Nets wrote about that. Jeff Oakes wrote about that. Perhaps also Victor, I don't remember, Victor, you will correct me whether this is true or not. The fact that inside Euclid geometry, there is a sort of, so to say, an aspect of Euclid geometry that is purely quantitative. So whether the objects are considered not for their position, but simply for their size. And this is also what is done in the solution of equation of second degree equation. Okay. And so this fact that you have some sort of algebraic kernel within the Euclid element made me and Radial Nets also to argue in different paper in different way that the origin of algebra is directly within the Euclidean geometry because this is an extrapolation of this purely quantitative kernel from a theory that is a geometry, so does not only depend on the measure, but depend also on the respective position of the object. But if this is true, this difference is already present in Euclid because this kernel is exactly the part of the geometry that does not deal with angle, but with sum of angle. It does not deal with segment, with the sum of segment. It does not deal with polygon by the sum of polygons. And so this distinction is already there in a distinctive way.
Because I don't see why the word sum, as it is used in Euclid's elements, has anything to do with addition. Simply asking that the two angles be put next to each other.
No. In a sense, yes, in a sense, no. There is no sum in the sense that there is no defined function as we consider it a sum to be, that is a total two-argument function, okay? And what you use is rather the conjunction, Greek conjunction chi, to take together. Chi means and. It does not say A plus B, it says take A chi B. And so in this sense, apparently, it's not thematized, to speak as Cavaliers, is not thematized as an operation. But on the other side, it's not true that you simply take two angles that are adjacent one to the other to consider that, because to make only an example, when I can make a lot of them, take postulate 5. Postulate 5 say if the sum of two angles is less than the two rectangle, then but the two angles are not adjacent. And they have not to be adjacent, because if they were adjacent, it would not be sensical. So postulate 5 say if the sum of this is less than two right angles, so this is a point of intersection. But the sum of this what does it mean? It's not an angle. And this is only an example. In many cases, he made something like that. That also, in the case that we make it not only for angle but the segment, when we speak of the triangular inequality, we're also speaking of the sum of two segments. It is not a segment.
Yeah, but so your question, I guess, has the logic that is behind what Euclid is doing being formalized, and then as Euclid's reasoning being formalized on top of that.
Okay, so this is an interesting point. So we are working on formalization of Euclidean logic, but this was the origin of the project. That was the start. In fact, now we start to think that what we are doing is formalizing mathematics, not formalizing logic. That in fact, the situation is not as has been very often described, that there is a very good logic and then you give the postulate and then Euclid go out from logic. Practically, there is not there is nothing as a logical system subjacent. There are a very few logic, a very weak logic, and a very strong mathematics in the element. The logic is very, very, very weak. No.
There is work that I was. I guess there's two strands. Satisfactory about which is why you're from project. But there is a theory that
So what they did in Avigad and Dean and Walter Dean and John Mumma, very nice paper appeared on the review of Symbolic Logic, is a paper where they gave a formalization of Euclid formalization. In a sense, you can say, ciao, the formalization of Euclid element where you eliminate the reference to diagrams and introduce all the postulate that are necessary in some sense. This is a very nice paper that I like very much and we used it a lot, but it's not the same project that we have, because our idea is to construct a setting using a rule of introduction or elimination for object. So not the logic, because the formalism is completely different. The formalism that is behind it is completely different.
It's constructive. You really want to
yes, our idea is to make as clear as possible the constructive character of the. In your construction, the constructive character is a little bit disappear.
But you mentioned the paper.
I arrived, sorry.
That would be a natural thing to claim. tempting when that's what people are doing, but you have these proofs by contradiction, and those are not regular. So it's something kind of in the neighborhood of regular.
Victor,
Yes, you mentioned this Avigad paper and so, but there is also Michael Beeson's reconstruction, right?
It's more constructive.
Which is very much based on constructions, yeah?
and there is also a paper by Beeson.
Yes,
He's referring to.
Yeah,
that's what I was referring to.
that's reasonable.
Yes, but also the point of Beeson. Beeson, for example, in his construction, use the null segment and the zero angle that seem to me not really be Euclidean. And so he has a strange argument about the postulate proposition 1-2 that say the postulate 1-2 is not constructive because apparently there is a two different construction according whether the point is you cannot superpose construct. The idea is the following: if you take two segment A, B to the point in C, if the point in C is one of the point A and B, so the algorithm is different. Okay. There is a sort of continuity argument there, but we think that these cases do not appear because we, in our logical system, two different letters stand for two different objects. So we have not identity. We cannot write something as A identical to B.
And Euclid never did, so that's.
And Euclid never did. So in fact, the case that according to him, the case of non-constructivity is the case that do not appear according to us in our setting of the elements. But this is not only the only difference. And also the difference in this Beeson speak. And we want to write a system that is completely implementable on a machine. Sorry?
We would like to do that, something that is checkable by a machine.
Oh, but and Beeson is not concerned with that.
No. Okay. Other questions? So, Victor, you think that it worked, this proof of postulate for?
Certainly, it worked well. Yeah, I didn't see any problem.
So if you say that it works, it certainly works.
Yeah.
Other question? We can stop here. Other question, remarks? The MPP students?
Can we say that the postulate first shouldn't have been actually a postulate?
Sorry?
Can we say that the postulate for the Euclid element shouldn't have been actually a postulate?
We can take it in this sense. No. What we say is another thing. What we say is the following. In Euclid, there are three sorts of liminary propositions. Postulate, common notion, we can also call axiomata with Aristotle argument, so we can call axioms in modern terms, and definitions. The relation that there is between definition and postulate of axiom in this system is very different than the relation that we have in a modern axiomatic system, because in a modern axiomatic system, definition has to be licensed by axioms. Here, the definition are completely independent of the axioms. So it is make already to say that Euclid system is not, in a modern sense, an axiomatic system. But okay, forget definition. That is a very nice subject of what is the role of definition in Euclid, but is not something that we consider today. So we consider a system with two sorts of axiom of liminary propositions, postulate of axioms. Postulate 1-4 is a postulate, but as the form of an axiom. Okay? And so this is the first strange thing. Why postulate 1-4 is not an axiom? An answer is that what we call axiom are axiom not because of their logical form, but their axiom because they are no common notion. So they are common to geometry, arithmetic, three-dimensional geometry, theory of proportion. So it seems that the distinction that Euclid is doing is not because of the logical form, but because of the range of generality. The postulates are particular to geometry, the axioms are general to any theory of quantities. Okay. Still, it remains a question that the postulate of 4 is different from any other postulate. has the form of a theorem, or if you want, of an axiom. So what we have proved, or believe to have proved, is that postulate 4 is provable. So, but it's provable under condition that we accept as a theorem proposition 1.4 and 1.8 that Euclid accept a proposition fact, but he proved by a method that are questionable. So if we want to eliminate the method of superposition, we need to take 1.4 and 1.8 are postulates. And so now we would have a system that is constituted by postulate 1, 2, 3, proposition 1.4, proposition 1.8, and we do not need the postulate 4 because postulate 4 is provable, by it is a 5. And this method would be, a system would be a system for absolute geometry. That is a geometry where there is at least one parallel, possibly an infinity of parallel, that is a geometry that is not Euclidean because it could be also Lobachevskian, but it's certainly not Riemannian, because for the Riemann geometry you have to eliminate also postulate 2. So what we call absolute geometry is a geometry where it's not established whether there is only one parallel or more. We have existence of parallel, but we are not unicity of parallel. So what we argue is that postulate 1, 2, and 3 plus proposition 1.4 and 1.8 without postulate 4 is a sufficient axiomatic system for absolute geometry. Correct?
I would say so.
Other question?
I think it's a long answer.
Wait, so you said with the project you guys are working on, you think now it's a formalization of all of mathematics?
Sorry?
Oh, no, just book one.
Oh, no, but I thought you said, I missed something you said. Never
So-
mind. I thought like the project that you're working on,
Yeah.
the idea of it is a little different than what originally.
No, okay. It's original, different because our initial idea was to construct a logic and to use a logic as we use today, or logic in a formal system. So what is a piano arithmetic? Piano arithmetic, first order logic plus proper axioms. So there is a clear distinction between what is logic, what is mathematics.
Right.
Or second order piano arithmetic, what is second order logic plus proper axioms. So this was the idea that we had in the beginning. We construct the logic and then we put the proper axiom inside and we have the element. And we discovered this apparently is not possible. So logic and mathematics are totally connected. There is nothing as a logic that is there before.
Pretty trivial.
Or if there is something, it's absolutely trivial.
Laws, I can sort of forget things.
Sure.
And that's nearly
No,
it.
yeah, that's, that was our, with Jeremy, that was our conclusion.
Divided into cases, and every time that a case gives you to a contradiction, you forget about that case. Essentially, that's the whole thing.
But all these contradictions are things like the trichotomy law, and those are mathematics. That's not, there's nothing logical about trichotomy.
In modern terms, the only thing that there is disjunction elimination. You cannot really say in this way because, but mutatis mutandis, the only thing that there is disjunction elimination.
Well, you still need a way to, like you're saying, it's regular logic, right? There's still, like, for all existing, something, right? Yeah.
You have to be able to state those things. That's right. That's reasonable.
Yeah. So that's not just.
So for example, we are in this logic, there is no, in this logic, there is no negation as a propositional connector. There is only atomic negation.
No, right. Yeah, absolutely.
So atomic negation is not really negation because it's a
Right. It's not first order logic in the sense that you don't.
there is no propositional negation. You have only if you want atomic negation of, if you don't want this another say, you have a simply incompatible predicate. That is the same thing. You have some incompatible predicate.
Right.
And so there is no conjunction, for example. You cannot conjunction, not propositional conjunction, in the sense that they can conjunct to actions, but you do not have conjunction in the proposition themselves.
Right. So you don't conjoin theorems. for instance, to get another.
So it's a very, 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 very weak logic.
Yeah.
Very weak logic.
Yeah.
Practically, there is no logic. There's mathematics direct. There is exactly the contrary of what generally said. What generally said is that you have a logical. Euclid is an example of mathematics, rigorous mathematics. Why? Because you start from the axiom, using logic, it prove anything. No.
In fact, that's exactly what started this conversation. Was
Exactly.
Marco and I
This was the origin of the conversation.
worrying about whether Euclid would he recognize modern mathematics, and would modern mathematicians recognize Euclid if they knew what he was really doing? In other words, are there different mathematics?
Right.
And my position was, no, there can't be. That was horrifying. And Marco's position was, well, maybe we should find out.
So yeah, let's look at it. So in the end, in the beginning, we disagree. And now I don't know whether we agree or not, but we will see in the end. I think that the end, now we are partially agreeing because we are writing a paper together. But when the paper will be published, I'm sure that we begin again.
Oh, yeah, 15 seconds later.
Well, it's just, you're just constant. It's not possible for you to agree with anybody. Right?
Sorry?
No, it's like a vacuum. There's something
You
there.
know, it's just
There's always something.
part of
there.
the essence of mind.
Yeah, of course.
Okay. No other question? So I remember to the MPP students, and Dominic disconnected, but if you meet him, tell him that you need to write a report and send it to me. Does not mean that you have to make it tomorrow. Does not mean that you have to make it 25 pages. But a short report of 5 lines, 1 page, what you want. You have to send me in the next 2-3 weeks. But if you make it this week, it's better, because then another week we have another. But I would not tell you, you did not send me the report. But you have to send the report. Okay?
So you talk for 2 hours or 3 hours? How much was it?
What time is it?
You talk for 2 hours and you only let them write 10 lines?
No, they write what they want. They write what they want. You want to write 20 pages, you write 20 pages. Okay. Thank you very much.
Thank you.